In this section of chapter 7, I would like to discuss about ionization energy, electron affinity, and reactions given by metals and nonmetals. Ionization energy. This is the energy needed to remove an electron from an atom. In case of a sodium, if you look at periodic table and find out electron configuration is sodium is 1s2, let me write down that on the top. So that's for sodium, 1s2, 2s2, you're on the line 2, 2p6, you're at the end of line 2, and then the first element in line 3, that's 3s1. So that's sodium. If I want to remove an electron from 3s, this electron, and that would be called first ionization energy. The energy needed to do that is 496 kilojoule per mole. Now, first time you are removing the outermost electron is first ionization energy. The second time you are removing is called second ionization energy. Third time you are removing it, it will be called third ionization energy. So that's how it goes. Now here we need to explain two things. First is from first to second there is an increase in ionization energy. Second to third there is another increase in ionization energy. Why ionization energy increases from first time to second time, from second time to third time. Secondly, we need to also explain why there is such a big increase. Now, whenever there is a formation of noble gas configuration, like in this case, after you remove the first electron, in case of sodium, let me write down sodium plus electron configuration with different color of the ink, 1s2, 2s2, 2p6, and that's noble gas configuration. You can find that that's the configuration of neon. Noble gas configuration is a pretty stable configuration. In other words, atoms would like to have that, atoms or ions. If you try to break that by removing another electron, it's going to resist that, and that's why you need some extra energy. So from first to second, that there is a normal increase, but beyond that would be whenever you are breaking a noble gas configuration. And that's why there is such a big increase from first to second ionization energy in case of sodium. Now, we are going to also explain to you from first to second, second to third, why there is always an increase in ionization energy. The answer you're going to get just by looking at the charges. First time you're removing an electron, you're creating a +1 charge, which you try to hold back the electron. Second time you're removing an electron, you're creating a sodium 2 plus, which you try to hold back that electron, second electron. So as you are knocking off electron one after another, the positive charges created would be larger and larger, and force of attraction trying to hold that electron would be larger and larger. So that means from first to second there will be an increased attractive force, so that's why you have to put extra energy. From second to third there will be another increase in attractive force, so you need to put extra energy. So that's why consistently ionization energy increases as you go from first to the second to the third and so on. However, there will be a big jump in increase whenever you are breaking a noble gas configuration. Here we are explaining the same thing. When first time you're removing from sodium, it becomes sodium plus. Second time you're removing an electron, it becomes sodium 2 plus. And third time it be sodium 3 plus. So there'll be an increase in ionization energy. Now in terms of electron configuration, I already mentioned this to you, that in case of sodium, whenever you go from sodium to sodium plus, you create a noble gas configuration. And from sodium plus to sodium plus 2, you're breaking a noble gas configuration, and it doesn't like it. And it tries to resist such a change. And that's why there's a substantial increase in ionization energy. Normally ionization energy, by looking at periodic table, is increases from left hand side to the right hand side of periodic table. So if you look at periodic table from left hand side to the right hand side, as size decreases, so that's the general trend of decrease in size. As size decreases, ionization energy increases. And it makes sense because electrons get closer to the nucleus and you need to put extra energy to remove those electrons. In addition to that, there are some cases, where I need to explain to you. If you have filled or half-filled sublevels, they're more stable than the neighboring configurations, and accordingly their ionization energy would be more in comparison with neighboring elements. So that's why beryllium, if you think about beryllium and nitrogen electron configuration, beryllium has half-filled 2s subshell, whereas nitrogen has 2p, half-filled 2p subshell, which we are going to show you next. Here we are showing you the electron configuration. Outermost electron configuration for beryllium is 2s2, and in case of nitrogen is 2s2 2p3. If you look at 2p3, there are 3 orbitals in 2p subshell, and they're singly filled. So if you think about 2p, let me write down 2p. These are the 3 orbitals, and there are 3 electrons, so they're singly filled, and that's why more stable. So keep this in mind. Completely filled subshell or half-filled degenerate orbitals represent greater stability compared to the neighboring configurations. So that's why normally you'd expect that nitrogen would be in between carbon and oxygen, but it is not. It goes over each of these. And same is the case, beryllium should have been in between lithium and boron, but truly it is even greater than boron. So keep this in mind about these trends. Now we are going to do now problem number 45, page 282. In problem 45, the question is, based on their positions in the periodic table, predict which atom of the following pairs have the smaller first ionization energy. So let's first do 45A. In 45A, question is between Cl and argon. So let's write down Cl and argon. It would be helpful if you look at periodic table at the same time. Now, Cl and argon belongs to period 3. Period 3 is same as line 3. So it's like this. Cl is on the left hand side and then argon is on the right hand side. Remember I mentioned that as you go from left to the right, ionization energy increases. So first ionization energy increases. So in this particular case, between Cl and Ar, Cl would have the smaller value of ionization energy. First ionization energy. So answer is Cl with the smaller first ionization energy. So let me write down here, IE increases. Now let's do, again, these are very similar problems. Let's do now D, 45D. In 45D, question is about sulfur and germanium. So 45D, sulfur and Ge. Again, if you look at their locations in periodic table, you can draw a line. That way it'd be a lot easier for you. So look at periodic table and draw a line starting from sulfur heading towards germanium. Sulfur is actually you can start with germanium. I think that'd be easier for you. If you have a germanium, now go along that line up to the group that has sulfur. So I would go like this, starting with germanium. So germanium, and I'm going to the right until I get selenium, which is the same group which has sulfur. Selenium, and then you go up. That has sulfur. Okay, again, this is the direction in which size of atom decreases and ionization energy increases. So let's write down here, ionization energy increases. What that means is germanium would have the smallest value here. So answer to this question is germanium. In this slide, we'll talk about electron affinity. Affinity means love for electrons. Now, fluorine, being so close to a noble gas, neon, which is only one electron away from neon configuration, it shows great affinity for electron because every element and ion would like to get noble gas configuration. Just to make sure that you understand that, fluorine has electron configuration of 1s2, 2s2, then 2p5 in line 2, 2p5, and corresponding noble gas neon has 1s2, 2s2, 2p6. So it's only away by one electron. And that's why fluorine shows affinity, great affinity for electron, just like a hungry dog would show affinity to grab the piece of meat. Now when it grabs the piece of meat, it provides calorie, and in the body of an animal, this calorie would cause exothermic reaction. That's how they maintain the body temperature, just like we maintain our body temperature. So in other words, this provides exothermic reaction. Keep that in mind. Similarly, fluorine, when grabs electron, energy is given off. So whenever it forms fluoride, heat is given off. So keep that in mind. Whenever there is an electron affinity and the electron lands onto that element that shows the affinity, energy is given off. Now, this is the case when there is no affinity. Like, you probably know that there are two kinds of dinosaurs. In one kind, they didn't like meat. So they are repelled by meat. Similar is the case with argon. Argon, having electron configuration of noble gas, because it's a noble gas, it doesn't want to have any more electron. So if you want to put any electron, you'll have to force it. Just like a kid who doesn't want to eat broccoli, and you're forcing the kid to eat broccoli, and he's going to throw up. So there'd be no such exothermic reaction in the body. So keep this in mind. Whenever you're forcing something, in case of an argon, you're forcing an electron to land onto argon. In that case, there'll be no energy given off. Rather, you need to put some extra energy. That's why electron affinity in this case would be measured by not a negative energy, rather a positive energy or equal to 0. If the hate electron, positive means hate electron, you need to force it to happen. So from our discussion, you know how we can measure electron affinity. So if there is an attraction for affinity of an element for an electron, it would be measured by how much energy is given off. More attraction, more energy would be given off. So keep that in mind. No attraction, electron affinity would be 0, or more than 0 plus means it, as I mentioned, it hates electron. It doesn't like to have that electron, and you need to force electron to land onto that element. General trend of electron affinity is same as trend in ionization energy. If you're looking at period of elements as you're going from left to the right, as size of atom decreases, electron affinity increases. Of course, in this case, even though the trend up to group 7A is going to be valid, but you cannot apply this in for noble gases, which 8A. So leave out 8A elements are noble gases because they don't follow this trend. As I just mentioned, noble gases don't like to grab any more electron because they're happy with their electron configurations. Now, within the trend from left to the right, there are some exceptions based on half-filled or completely filled subshell, similar to what I discussed in case of ionization energy. So beryllium has 2s shell filled and nitrogen has half-filled p subshell. So keep that in mind. So half-filled or completely filled subshell can provide greater stability in comparison with neighboring elements in periodic table. We already talked about noble gas. When you try to put an electron, it would not like it, and that's why it's going to be greater than 0 because you're forcing it to happen. In this table, you're looking at electron affinity values of different elements. Electron affinity is measured by how much energy is given off. That's why these are negative numbers. Now, of course, there are a few exceptions, so leave out this group, nitrogen, and of course the noble gases noble gas elements don't like to grab any electron, so they're all greater than 0. And in some cases we can explain this exception because of half-filled or completely filled subshell. So let's leave out beryllium group, boron group, and nitrogen group. Others follow the trend. As you go from left to the right, the negative electron affinity, negative means affinity for electron because energy is given off, is increased. Now we are going to discuss different reactions given by metals, non-metals. Now metals like sodium, when reacts with oxygen, it gives you sodium oxide. Be careful in writing down the formula. This is how you can write down always the right formula. Sodium, when it makes a compound, it's +1. It's from group 1A. Oxygen from group 6A gets -2, and that's how they combine. And this 2 from oxygen goes down to the bottom of sodium. This 1 goes down to the bottom of oxygen. And that's how we get Na2O. So always think one element at a time, side by side, with their positive and negative charges, and that's how you can write down the right formula. For non-metal like carbon, sulfur, they can give you carbon dioxide, sulfur dioxide, usually more than one such compound, sulfur trioxide. These are non-metallic oxides, and sodium oxide, calcium oxide, those are metallic oxides. Metallic oxide in water gives a base. Think about sodium oxide with water gives sodium hydroxide. That's the base. Non-metallic oxide, on the other hand, would give you an acid. Like sulfur dioxide in water gives sulfurous acid. Sulfur trioxide with water gives sulfuric acid. And that's the cause of acid rain, because in rainwater, we often have sulfuric acid, because in atmosphere we often have sulfur trioxide coming from industrial pollution. Now metals reacting with hydrogen gives metallic hydride. Now so far we discussed that hydrogen is +1 in most reactions, but in some cases hydrogen is more electronegative than the metal. So sodium hydride, sodium is plus, hydrogen is minus. Calcium hydride, calcium is +2, hydrogen is -1. So keep that in mind. In hydrides, hydrogen is -1. Now metals can react with halogens. So magnesium with Cl2 gives magnesium chloride, sodium gives sodium chloride. Again, be careful when you write down a formula. Even though reacting with Cl2, you can think it this way. Sodium is +1, and then rather than writing down Cl2, just write down 1Cl, and that gives you NaCl. In case of magnesium chloride, Magnesium is plus 2, 2 plus, Cl is minus 1, so it gives MgCl2. That way you're not going to make any mistake. Non-metal can also react. Hydrogen plus Cl2 gives HCl. Of course, we haven't balanced these reactions. If you want, you can balance them. If you want to balance, there'll be 2 in front of it. So same is the case other reactions that we discussed in this section. Ozone formation. In upper atmosphere, oxygen, 3 moles of oxygen or 3 molecules of oxygen combined together gives 2 moles or 2 molecules of ozone. Lightning usually helps in the formation of ozone. On the other hand, fluorochlorohydrocarbons are responsible for depleting ozone. Next, noble gases. Most of the noble gases don't give any reaction, but the larger noble gases like radon, xenon, they react with fluorine, giving series of compounds. Radon difluoride, tetrafluoride, etc. Xenon difluoride, tetrafluoride, hexafluoride. So those are the products of reaction.